Okay, let's jump straight into this explainer, because we're going to tackle a scenario that honestly probably keeps a ton of system architects up at night. We're living in this era where the pressure to ship features at absolute lightning speed is just immense. We all want to handle massive refactoring debt at scale, and obviously the natural evolution there is to hand over the heavy lifting to our tools. We want to confidently hand autonomous AI agents the keys to our code bases so they can just build, refactor, and test around the clock. But, and this is a huge but, how do we actually do that without losing sleep over what they might accidentally destroy in the process?
Right, so you know exactly the feeling I'm talking about here. You issue this incredibly complex prompt to your agent. Maybe you're asking it to do something massive, like migrating a complex database schema, or updating core dependencies across, say, dozens of interconnected microservices. You hit enter, you step away for a well-deserved coffee break, assuming the machine is doing all the hard work for you. But then you come back and you find your production repository completely corrupted by a hallucinating agent. Your terminal's just bleeding write errors, and it's a complete disaster. So how on earth do we architect our systems to prevent this specific nightmare from ever happening?
Section 1. The autonomous coding risk.
Okay, so to truly scale AI engineering, we have to make a fundamental shift, right? We're transitioning from manually typing syntax line by line to supervising autonomous agents. And while that's incredibly powerful, delegating control naturally introduces some massive execution risks. When you rely on a continuous loop of reasoning and acting, which we usually call a react loop, an agent can get stuck really fast if it hits an unexpected error. It makes a bad assumption, it tries to fix it, fails again, and suddenly, boom, you're caught in an unrecoverable hallucination loop. It's just piling bad edits on top of bad assumptions, mutating files all over your directory. And honestly, what's even worse is finite context window decay. That happens when the agent generates so many errors and bad attempts that it completely fills up its token limits. It effectively forgets the beginning of your prompt and the core codebase context entirely. At that point, it's just flying blind and chewing through your entire token budget.
Section 2. Local versus worktree mode.
So how do modern tools, specifically the Antigravity CLI, solve this underlying anxiety? Well, they do it through a pretty brilliant architectural choice regarding execution isolation. Picture this. On one hand, you have local mode. Using local mode is literally like handing the agent live ammunition right inside your active folder. It edits straight on the main workspace folders directly, meaning it can super easily overwrite your uncommitted active work. But on the other hand, you have worktree mode. When you choose this, your main directory branches off into a completely clean, isolated secondary workspace. You are moving the agent into a blast-proof sandbox operating in an isolated Git worktree, totally decoupled from your main directory.
Section 3. A destructive refactoring test.
Let's actually test the boundaries here with a real-world scenario. Imagine asking the agent to execute a highly destructive refactoring inside that isolated environment we just talked about, say, migrating the entire authentication middleware of your application over to JWT. That's exactly the kind of task that touches a ton of sensitive files and is highly prone to catastrophic failure. But when you issue that prompt, the CLI doesn't just start blindly deleting and rewriting code. Instead, it kicks off this rapid-fire loop: observe, plan, act, and verify. Now, what's super interesting here is the transition from step 1 to step 2. During the observe phase, it handles context assembly, gathering up the state of your code base. But before any tools are even invoked in the act phase, it transitions into the plan phase. It generates structured implementation artifacts, like a markdown plan detailing exactly what it intends to change. So you're getting a highly structured intermediate deliverable instead of just an unbounded stream of unpredictable terminal commands.
But let's say you approve the plan, you let it run, and things go horribly, horribly wrong during the verify phase. Maybe there are missing JWT dependency packages, and the agent causes AST transform errors right in your main server file. You'd start seeing linter panics flashing across all your auth endpoints. You'd watch the test runner fail recursively as the dependency upgrade just spirals completely out of control, triggering cascading errors. The agent tries to self-heal, but instead it falls into a panicked, unrecoverable hallucination loop right there inside the isolated environment.
And just as you think it's going to run forever and completely drain your API account, it hits a hard stop, the number 5. The system hits a strict maximum iteration cap of exactly 5 loops. This is a deterministic circuit breaker. It is explicitly designed to halt the agent the exact moment it detects a runaway failure loop, stopping it dead in its tracks before it burns through your quotas or degrades the codebase even a single step further.
Section 4. The Shadow Checkpointer Rescue.
Okay, so the code in the sandbox is an absolute mess right now, but you need to get back to work seamlessly. Right at the peak of the failure, you are saved by a truly brilliant piece of architecture. It's called the Shadow Checkpointer. By definition, this is a persistent engine maintaining shadow Git branches, file system snapshots, or temporal workspace directories to secure state before agent execution. In plain English, that means it was quietly maintaining a snapshot of your codebase, creating temporal directories the exact millisecond before you hit enter on that destructive JWT prompt.
Let's actually track how this plays out on a timeline. At t-0, we have our clean, pre-prompt checkpoints safely stored away. At t+1, the agent starts aggressively mutating files during the refactor. By t+2, we hit that critical failure, AST errors everywhere, and the circuit breaker trips. Then, at t+3, you simply step in and type the /restore command. And just like that, time cleanly rewinds. The corrupted files snap back to their exact pre-prompt checkpoints from t-0, leaving your production repository perfectly safe and completely untouched.
I absolutely love this quote from the documentation because it hits the nail on the head. You can revert state to the exact pre-prompt checkpoint without polluting your Git history. That is massive. You gain the absolute power of speculative design. You can fork branches and try out massive, destructive architectural ideas with total confidence. If the agent fails, there's literally no trace of the mess. No messy revert commits, no complex Git bisects, just a clean slate and fearless experimentation.
Section 5. Trusting agents at scale.
Now that we have this incredible safety net, and we know we can safely delegate complex tasks and actually survive critical failures, we can start applying this to enterprise systems. Once you establish that baseline of safety, you can deploy multi-agent topologies with total confidence. A lead orchestrator can sit at the top of a hierarchical structure, optimizing for context isolation and a clean separation of concerns by dispatching isolated sub-agents to perform those sandboxed refactors in parallel. Or maybe you use horizontal topologies, which rely on peer-to-peer agent discussion to provide multi-perspective code reviews. For high parallelism and decoupled execution, you might even employ a blackboard architecture utilizing asynchronous global state access.
But listen, to manage all those agents across any topology, you absolutely must establish rigid verification boundaries. By combining the worktree isolation we discussed earlier with programmatic post-execution hooks, like automatically running linters and static analyzers the exact moment an agent finishes its task, you ensure that absolutely zero hallucinated code ever reaches your production branch. You are enforcing a strict zero-trust policy for agent outputs until they demonstrably pass your deterministic tests.
Implementing these operational paradigms is really what sets the pros apart from the amateurs here. It means anchoring your system with mandatory declarative rules in a .agents directory, setting those firm guardrails from day one. It means explicitly setting strict loop circuit breakers and max iterations so you never accidentally burn your quota on a hallucination. It means utilizing that /fork command for speculative architectural threads, guaranteeing complete safety during exploration. And crucially, it means strictly enforcing plan review modes before any destructive actions occur, keeping a human comfortably in the loop. Mastering these specific controls is what transforms you from a manual syntax writer into a true systems architect.
So, as you transition into this incredibly exciting new era of terminal native engineering, what guardrails are you going to put in place? How will you architect your team's safety nets so you can finally embrace truly fearless refactoring and let your agents explore without limits? It's a fascinating challenge, and the coolest part is, the tools to solve it are already waiting for you right there in your terminal.